Thank you. All right, let's keep going. All right, so let's talk about the basically the continuation. So that's the case here. I hope you got a chance to read it. So a 7 month old baby is admitted in the hospital for bronchitis. He was noted to be about 15% of his body weight. So shortly after discharge, he began vomiting again, occasionally, and stopped gaining weight. Now, at 9 months old, so he was readmitted in the hospital. Okay. So when he was admitted, there was no abnormal, physical sign basically, and the blood and the urine analysis and the radiography was all normal. Okay. Now 1 week later, he became habitually drowsy. His temperature rose to 39.4 degrees Celsius. The pulse became elevated and his liver became enlarged. Okay. At this time, he slipped into a coma. So the person has a large liver. That's something to notice, okay? And now he's in a coma. So all standard biochemical tests were normal, but the electroencephalogram with EEG were grossly abnormal. Okay. Now the patient was given an IV fluid, glucose 81, basically glucose IV, and he improved rapidly and came out of the coma after 24 hours. So now urinalysis using HPLC shows elevated level of glutamine, hemoglobin, orotate, now new stuff for you. But the serum ornithine and ammonia level were elevated, okay? So what's going on with this patient? Is anything you've seen so far that give you a little bit of suspicion? Glutamine is elevated and the ammonia level were elevated, right? So it was concluded that it's an enzyme called the ornithine transcarbamylase, the deficiency in this case. So it could be any of the enzymes, in a urea cycle. And again, the urea cycle, as I mentioned earlier, that's when you get rid of a urea. And we're going to talk about it. So in this case, the patient has an issue, basically seem not to be getting rid of the glutamine, because glutamine is accumulating, right? And ammonia also getting accumulated because the person's not able to get rid of his ammonia. So it could be some problem with the amino acid metabolism, or at least getting rid of the ammonia. So the ornithine transcarbamylase deficiency, basically this is an excellent genetic disorder, deficiency on the urea cycle that we're going to talk about. Okay, and these are the symptoms. The person, when they have deficiency, the ammonia level goes up, and that can lead to a lot of issues. The symptoms are lethargy, vomiting, disorientation, somnolence, coma, and cerebral edema. Okay. So what is the urea cycle? There so much says about it. But it turns out if you put the whole thing together as a big picture in this case, you get amino acid from different sources, from your diet, but you also get it from degradation of your proteins, right? And what do their degradation generated? Let's do it together. What is generated? You have ammonium generation from ammonia, right? And you have to get rid of that ammonia. Now, as I said, ammonium because of the pK value. So now it can be utilized for other biosynthetic processes, okay? Because some other biomolecule inside your cell do need, amine group in order to be synthesized. So your body will use some of the ammonia for that. But the remaining you have to get rid of them, okay? The first molecule formed is a carbamoyl phosphate, okay? So once the carbamoyl phosphate synthesis, and this step is very important, we're going to talk about it, keep that in mind, and it's highly regulated. So once the carbamoyl phosphate is generated, this carbamoyl phosphate then get into the urea cycle. At the end of the day, the urea is generated, and once the urea is generated, you have to get rid of that urea, okay? And this is an important step process because I said ammonia is toxic. It's a potent neurotoxic molecule, so your body has to get rid of it, okay? So now, again, back to the, let me ask you a question. When the ammonia is generated from degradation of amino acid, what happened to keto acids? Make a connection. It's right in front of you. It get into the Krebs cycle, right? So make a connection. Make a connection. That's important, okay? Now, you get rid of it, but you also get the energies out of those molecules. So this is what we're going to focus on now. All right. So source of ammonia, we already discussed this, right? Glutamine, where does glutamine come from? Where glutamine come from? Tissues, right? It is generated when an additional amine group gets attached to the glutamate. How glutamate is formed? Glutamate accepts amine group from the surrounding, right? Or from another amino acid, right? So then the glutamate is formed, and that glutamate can accept another amine group and then get transported out as a glutamine. Now, alanine also the transport mechanism, as you recall, from the muscle, right? And we discussed that. So these are the two major sources of ammonia coming from different tissues and all the way to your liver, where they're going to dump the amine groups in forms of ammonia, and then it has to be excreted as a urine. So it comes from different sources, okay? All right. So now, as I said, this process generates a lot of ammonia, and ammonia is toxic, you gotta get rid of it. But you see the alanine coming in also can give this amine group to the alpha-ketoglutarate group and back and forth. So you generate a lot of ammonia this way, okay? Again, remember, glutamine has two ammonia amine group attached, okay? So that's your urea cycle and everything else associated with that. All right, so the urea cycle. So much said about it. You ready? All right, so let's pay attention here, okay? It turns around, you know, we said a lot generating a lot of these guys. What is it? Ammonia, right? You got to get rid of this ammonia. So the first things occur, you need energy for that process. You also need CO2. Again, this is the bicarbonate, but it is a dissolved CO2. Students tend to be confused that basically anytime you see this, it is a CO2 that is dissolved in the water, okay? So when you get a questions, don't forget that this is a CO2, all right? And then the amine groups, and then you have ATP here. Now, these three molecules has to be involved in the reaction. And this reaction is catalyzed by this enzyme here, carbamoyl phosphate synthetase 1, okay? So once that enzyme catalyzes the reaction, so you have what's called the carbamoyl phosphate formation, okay? So this is your carbamoyl phosphate here. Now the carbamoyl phosphate, once it's generated, can combine with what's called ornithine. And ornithine is like, if you recall the Krebs cycle, the original oxaloacetate, right? Then combined with the acetyl-CoA. But in this case, it's the ornithine that is originated. If this is a urea cycle, this is ornithine that is originated. And that ornithine then interacts with the carbamoyl phosphate to form what's called the citrulline. Okay? So citrulline, it's ornithine plus the carbamoyl phosphate. Now, these all processes here take place in the mitochondria. Okay? So now, once the citrulline is formed, the citrulline is taken out outside of the mitochondria, and the rest of the process takes place in the cytosol. Okay? So now, once the citrulline is generated, and citrulline now combined with aspartate. Okay? And once that interaction occurs, arginosuccinate is formed. But let me bring closer so you can see the whole process closer. So you see here on a larger scale, because it was small on the other one. I just want to see the big picture. So this is your carbamoyl phosphate that's generated from here. Now the citrulline, this ornithine combined with the carbamoyl phosphate, now your citrulline is the one that's coming outside. Okay, and as I showed the previous slide, the citrulline has to accept now the aspartate, incoming aspartate. Okay. Now remember, in the case, okay, what was going on with this patient? Did you remember one molecule was elevated? Huh? Ornithine was elevated, right? Right, because once the mutation occurred here, and these have, this is the enzyme that was affected, right? The carbamyl carbamylase, ornithine transcarbamylase. This enzyme is deactivated due to a mutation. The ornithine will accumulate, okay? And ornithine can be converted to orotate. And I'll have a slide close to the end, and I'm going to show you that. But for now, keep in mind, ornithine is elevated, and then that can lead to other issues associated. Okay? Everybody see the enzyme? All right. Good. So now, citrulline is formed. Okay. So once the citrulline is formed, the citrulline comes out of mitochondria. The citrulline now interact with the aspartate, and arginosuccinate is generated by the action of this enzyme called arginosuccinate synthetase enzyme. Okay, so that will lead to the formation of arginosuccinate. Okay. Now, one thing you have to remember here: the first amine group, ammonia, was floating around, right? Okay. You remember I said earlier the urea contained 2 amine group. Okay. Now the second one is coming from the aspartate. Where is it? Here, right there. Keep that in mind. Okay. And where did the aspartate get its amine group from? Can aspartate just picked up? Okay, you accept it from an aminotransferase, right? So basically, somewhere alpha-ketoglutarate have accepted an amine group from some and pass it on to to oxaloacetate to form aspartate. Now that's when the aspartate come and give the amine group now to the system. You see here, the glutamate that have accept amine group either from another amino acid or from the surrounding now pass the amine group to oxaloacetate, and you have your aspartate. Now that aspartate now combined with the citrulline, and now that's why you have what's called the arginosuccinate. We're very close to the end, okay? So you see the arginosuccinate. So arginosuccinate, when you look at it close enough, this is what? If you know your amino acid structure, this will be your arginine, and this will be succinate. The combination of aspartate and citrulline give you what's called arginosuccinate. Now, the succinate portions is going to clip off just in forms of fumarate, which is here, okay? So now you're clipping here, so that generates your fumarate. Now this molecule is now arginine. Everybody see arginine? What is arginine? You know arginine, right? It's an amino acid, right? And it's a basic one. This is how you generate an arginine in your cell, right? But this is how you get it off your... Now the arginine, if you look at the tail area of the arginine, so you have hydrolysis using water, and this is your urea, okay? So the tail of, if you cut the tail of the arginine, then that's your urea, okay? And then now you get rid of your urea, and that will regenerate ornithine, and ornithine get back in the mitochondria and accept another carbamoyl phosphate, combine them to form citrulline. Is that clear? It's not as complicated as the Krebs cycle. It's a little, but very simple, okay? So where does what molecule generate the urea directly? Look at it, something right there. Arginine, right? So it's the tail, urea is nothing else the tail of the arginine. So it clipped off and utilizing water, and that's your arginine right there, and it continues to recycle. So you want this cycle to be really fully functional if you want to get rid of your ammonia. So if you have mutation on any of these genes, you can find yourself in trouble. Okay? Is this clear? All right. Now the regulation, we always talk about regulation. All right? It turns out the carbamoyl phosphate is the rate determinative. Okay? It's a very, very important enzyme. And that's what we said earlier, the carbamoyl phosphate synthetase 1. Okay? Very, very important. And that is where, to put together, is this guy. Okay? That initially combined the CO2 with ammonia, and ATP is, basically for energy purpose. Okay? Now, the carbamoyl phosphate synthetase is stimulated by the molecule N-acetylglutamate. Okay? N-acetylglutamate is synthesized by an enzyme called N-acetylglutamate synthetase. So when you have a lot of N-acetylglutamate, that will stimulate carbamoyl phosphate activity. So you have a carbamoyl phosphate synthesis. Once the carbamoyl phosphate synthesis, you go to the urea cycle. Okay? Now, remember, when the enzymes is defective and you have an accumulation of carbamoyl phosphate, okay, and the carbamoyl phosphate, for some reason, if this enzyme is defective, the ornithine transcarbamylase is defective, that can lead to accumulation of carbamoyl phosphate. That can lead right to the uric acid. Okay? So when the molecule here, carbamoyl phosphate accumulated, so the level rises in your blood if this enzyme is defective, which we see in this case. You remember the patient has an uric level high. If you look at the case, okay? Look at the case, you see uric is high. So because the fact that the enzyme, not only ornithine is up, but also the fact that the carbamoyl phosphate is also elevated. But this guy take another route, and then that will lead to the uric acid formation. And this is sometimes you see in biochemical reactions. When you block enzymes and the substrate build up, the substrate will try to take another pathway. Okay, so keep that in mind. And that's why you see sometimes when you, especially for you as a clinician, if an enzyme defective, they tend to look at a byproduct that normally is not present. And then if that level is elevated, which means most of the time, the enzyme, in front of it, probably not functional. So if the substrate accumulated because the enzyme not functional, this substrate will not sit there just like that. What it will do is to find another pathway. Just like when you're on a roadblock and you see a little place where you can take off, you will take off on that one so you can keep going, right? Somewhere. So exactly the same thing. You have a roadblock here. The carbamoyl phosphate level goes up, and that's why you see a lot of uric acid accumulation on the patient blood. Okay? Now, N-acetylglutamate being the activator of the system, and N-acetylglutamate synthetase being the molecule that synthesizes the N-acetylglutamate, and these are synthesized from glutamate and acetyl-CoA. Just like the name indicated, you have a glutamate and acetyl-CoA, they're combined to form N-acetylglutamate. Now, the N-acetylglutamate synthetase activity is stimulated by the molecule called arginine. Okay? Does that make any sense? Why arginine will stimulate this? You remember arginine? Did you see arginine before? And arginine is what? So which means you have a lot of substrate sitting in there. So arginine will stimulate this guy. Listen, you have to keep pushing this guy. The enzyme, where is it? Yeah, you have to keep pushing this guy. So once this guy activity goes out, he will push this guy to be activated to synthesize this guy. So this guy can activate this guy. Is that clear? Maybe, should I call them by name? All right, here is the deal. Arginine means you have a lot of substrate for urea, right? And you want to get rid of your urea. But one way to get rid of urea is to stimulate urea cycle. So high level of arginine is sensed as a need for urea cycle to be stimulated. Is that clear? So when you have a high arginine level stimulate this enzyme. So once the N-acetylglutamate synthase enzyme is activated, so you have increased accumulation of the N-acetylglutamate, which will then stimulate the carbomoyl phosphate. Now you have a carbomoyl phosphate synthesis. And this reaction is the rate determining step of the urea cycle. So once you have a lot of carbomoyl phosphate, then the reaction keep going. Is that clear? So that is why arginine it doesn't directly, but it go and activate this enzyme. So the whole system is now geared up. Basically, it means that arginine level is here high. We are now ready to get rid of your urea. Okay? Is that clear? All right. Now, this is put the whole thing together. As you see here, basically everything we said, this is a urea cycle. And then aspartate is generated. Aspartate brings the second amine group. You remember that? The first one comes from where? The first one comes from where? The free ammonia, right? All right. Let me back up a little bit. The first amine group in the urea comes from where? Free ammonia, right? Carbomoyl phosphate synthesized. Where does the second amine group in the urea come from? Aspartate, right? And where does aspartate have gotten his amine group from? Alpha-ketoglutarate. And where did alpha-ketoglutarate get his amine group from? Either from an incoming amino acid or from the surrounding ammonia. Does that make sense? So basically, it's using two ways in order to collect amine group and then put it into the urea to get rid of them. So one way to get rid of the urea amine group very fast. Is this clear? It looks little, but it's not. Once you start reading it, it starts making much more sense to you. All right? So as you see here, basically that's what it is. The aspartate will bring the second amine group, and the first amine group came from the ammonia that is floating around, and that ammonia is combined with this CO2, and ATP is used on that system, carbomoyl phosphate, then that will all, bring out the first amine, and the aspartate will bring the second amine. Is that clear? CO2 is involved, and ATP is involved. So it is an energy requirement reactions. Is that clear? All right, so that's the for urea cycle. It's not much, right? Good. All right, so let's talk about some disorders. Amino acid metabolism disorders. I think that's probably a little fun for you. So there are over 50 amino acid metabolism disorders, but we're going to talk about just a few of them, okay? Yeah, you can wake up now because this is kind of a little bit interesting, okay? It's not too much cascade to it. All right, so even though they're not a single one that are not that big, but if you combine them together, so it becomes very important issues in terms of the newborns issues, okay? And one important one is the PKU, phenylketonuria, associated with phenylalanine metabolism disorder, okay? And one thing you have to remember, even though they look like not that, but most of them lead to mental retardation and the development delay, which is not something fun to have when the child, that you love so much is there having this deficiency. Is that clear? Okay. Now, the phenylketonuria, PKU, phenylalanine is an amino acid, right? Now, you can generate a tyrosine from phenylalanine, and the reaction is very simple. You just add a hydroxy group right there. So phenylalanine, you attach a OH group, and that is your tyrosine. And that is catalyzed by an enzyme called phenylalanine hydroxylase enzyme, okay? So the only thing the enzyme does is add the OH group, but it requires the cofactor, the tetrahydrobiopterin, okay? So now, you can generate tyrosine from phenylalanine. You know that now, right? So phenylalanine is essential one, but the tyrosine, is tyrosine essential amino acid? Yes or not? No, because you can synthesize it, right? Through this reaction. So it turns out the PKU is involved with this enzyme. The disease, when you have a mutation in this enzyme, and the enzyme is coded, this is the chromosome location, chromosome 12. So when this phenylalanine hydroxylase enzyme is deficient, so phenylalanine accumulated in the blood, right? Does that make sense? Because you cannot convert it to, how about the tyrosine? Is tyrosine level going to be high or low or normal? If you're eating a lot, yeah, but if you're not synthesizing anymore, so it starts dropping, right? So the enzyme deficiency not only induces accumulation of phenylalanine, but deficiency in tyrosine, all right? But it turns out the enzyme may be normal, okay, but there are other disorders. The cofactor, if the cofactor level is now high enough, for some reason, you'll not be able to take your cofactors and utilize them in the process, and that can lead to other disorders. The tetrahydrobiopterin is also involved with other reactions, such as we have here. You see, this is the tetrahydrobiopterin, the BH4. As I said, is involved with the phenylalanine hydroxylase reaction to form tyrosine. But it's involved with others processes. Now, you probably didn't see this before, but you can synthesize your catecholamines, which is your adrenaline, epinephrine, norepinephrine, dopamine. You can generate them from tyrosine. Did you know that? Okay, all right. So those molecules called catecholamine, you can generate it from tyrosine, but the reactions require tetrahydrobiopterin. But this enzyme called tyrosine hydroxylase, even though the enzyme is fully functional, but if you are deficient on the tetrahydrobiopterin or the enzymes called the dihydrobiopterin reductase that regenerated the tetrahydrobiopterin, if that enzyme is deficient or for whatever reason you're not getting enough substrate, then that can lead to something similar to PKU. Is that clear? So now, but for instance, in the serotonin synthesis, serotonin is a neurotransmitter as well, right? So now, serotonin is synthesized from tryptophan, and tryptophan is another amino acid, right? And the tetrahydrobiopterins, it's a cofactor for that reaction, the hydroxylation reaction, so that lead eventually to the serotonin. So if the cofactor is deficient, so you can be deficient on all of these products, right? Okay, you won't be able to synthesize it, okay? So not only the enzyme deficiency causes disorder, but the cofactor deficiency also. And that is very important. And you had a whole lecture on vitamins. And these things, you need to know those things, being a clinician. Because you may see people with the deficiencies in these vitamins. Maybe not so much in the US, but if you're serving outside in developing countries where people don't even have enough to eat, even less having a balanced food, they can be deficient in these cofactors in forms of vitamin. Is that clear? Good. So the PKU, as you see, now in the classic case, basically the enzyme is deficient. So phenylalanine will accumulate in the blood, right? So once you accumulate it, so the phenylalanine, as I said earlier, once you block the road ahead of you, people, they will try to take off on the road, right? So the phenylalanine, when it accumulated, now what happened, it will take off. The phenylalanine level rise up, it will take off in different direction. So you have a phenylactate and phenylacetate formation. And these molecules are not too much of your friends. When they accumulate in the tissue, they can cause issues for you, okay? So now, the fact that the phenylalanine give rise to tyrosine, and tyrosine, if you look at it here, some of those molecules require not only catecholamine, but also melanin. Everybody know melanin? The molecule that make your skin color. So basically, the fact that the tyrosine is a precursor for the synthesis of melanin. If the patient have a deficiency in the enzyme, now not only you're going to accumulate all those molecules that it's not too friendly in your body, but you also will not be able to synthesize any of these products, including catecholamine and melanin, so the person will have kind of a fair skin color, and other molecule will not be synthesized. Okay? So as this young lady has a completely lack of melanin on her skin due to the deficiency in hydroxylase. And this is slightly different for other called the albinism as well, right? The albinism, there is a tyrosinase, and we have a full lectures on that in the, I think, second year. All right? So that's why we didn't talk about the albinism here. But this one is just the hydroxylase. So because of these molecules accumulate in the blood, so it gives a little mushy odor on the urine, because once they accumulate, the fact that they're water soluble, they can leak out in the urine, so they get concentrated in the urine, and that will give a mushy odor in the urine. All right? And in this disorder, I think you're going to see it even more in metabolic disorders and so forth. So this gives you a little bit of background, and so for better clarification later on. Okay? Is this clear? Yes? In the PKU? And PKU is very, very important because, it's infants in the U.S. get tested for these issues, at birth. They get tested for it because there are ways to take care of them when they're found positive for the enzyme deficiency. So now the issues, the newborn screening, so help you to identify the child earlier. If your baby has the disorder, it turns out the IQ level drop as they grow because you have, okay, let me back up. The IQ decrease because of what? Yeah, you have an accumulation of those byproducts. And once those accumulate, they can cause a different issue. The IQ drop as time goes by, and the patient become mentally retarded or some kind of issue associated with accumulation of those byproducts. All right? So now, he thinks these are some of the symptoms associated with it: mental retardation, failure to talk, tremor, growth failure, and so many others associated with accumulation of those byproducts that I showed you earlier. Now, for the screening, it turns out in the U.S., all babies are screened at birth, okay? But one thing you have to remember, they have to repeat the screening again, because what happened, the placenta is very good at getting rid of the phenylalanine, okay? So phenylalanine, you may not see phenylalanine accumulation right away in a baby when they're just born, right? But a week later on, when the phenylalanine, so the baby relies on his own system, the phenylalanine start getting accumulated, and then that can take over. Then you can see issues just the week after the baby is born. So it's required, clinician probably tells you a little more. So once the baby is born, it's tested. If it's negative, you test it again a week later on. Now if it's negative, so which means it's okay. But if the baby is positive, then you will check it again a week, it's most likely going to be positive again. And then you have to put on a special condition in order to hand up to take care of the baby. And that includes holding phenylalanine from the food. Okay? So for the treatment, as I said, now you have to feed the baby food that is really rich or poor in phenylalanine. Poor, right, exactly. So you're trying to, sometimes they have a special food that is synthesized for the baby to try to hold on and decrease the phenylalanine. But as I say, phenylalanine is an essential amino acid, so you should have in your diet somehow, but in a lower amount. So you would not have excess to get rid of, okay? So these are some of the food that you probably need to stay away from. Meat and starch, fish, they are very rich in phenylalanine. So you may want to get, you probably got some specific food there now that you can give to the baby that are very low in phenylalanine. So to basically decrease the accumulation of phenylalanine so those byproducts will not be formed. Is that clear? So the next one is the maple syrup urine disorder, disease associated with these amino acids. You know these three guys, right? So now, again, you have to get rid of your amine group before you utilize them. But there are other processes they have to be they have to go through, and specifically there is a step where the enzyme called the branched-chain keto acid dehydrogenase enzyme, which catalyzes also the step on the metabolism process. And when this enzyme deficient, So it leads to this maple syrup disease that we're going to talk about. Okay, so it is a recessive autosomal recessive disorder. So 1 in 180, almost one every 185 children may be diagnosed with it. Okay, and they're associated with deficient, and they're called the branched-chain amino acid. That's where the name came from. Is that clear? All right. So these leucine, valine, isoleucine, so they go through a metabolic process. But at one point, if you are deficient on an enzyme called the branched-chain keto acid dehydrogenase, so they will be stopped at this point. They will no longer go young and continue on the degradation process. So when that occurs, you have an accumulation of a different byproduct, as you see here, and they can take off in different directions. Okay? So this is called the maple syrup disease. If you take the urine sample of the person, they used to test it by testing it to make sure. That's back in those days, how to diagnose the disorder. Yeah, I know. So the test has, the urine has a test on it. That's why it's called the maple syrup disease. Yeah, back in the doctors, just want to diagnose the patient, right? I'm not asking you guys to do that. So that's what I used to do back in early days when they identified. And they said, basically, how do they know? Patient who has this disorder, when they urinate on the floor, there is these kind of ants, I don't know if you guys know it, that are attracted to sweet. You guys, if you have a sweet, stuff on the floor, you don't see it in the U.S., but outside, I know in Africa you see it. Once you have a sweet stuff on the floor, you have for instance, a coffee that has a lot of sugars and you pour on the floor, and you will see those ants crawl to it. They like sweet. And if you open a container with honey or all those stuff, they will get into it, and they will even die inside to tell you how much they like sweet. So when the kids used to urinate on the floor, they were so sweet that these ants were attracted to it. So that's why they know maybe there may be some sweet in the children's urine, and that's why they find out that it is in fact sweet. And the doctor, since they don't have any method so they used to test it out to make sure that it's not that case, or if it is, for diagnostic purpose. Is that clear? Any of you seen that ant before? Anybody? You've been seeing it? Yeah. Good. All right. So the intermediate would accumulate just like I said in the other case. Okay. So now, in order to treat the patient or prevent it, what would you do? What would you do? You have to try to limit the intake of those branched-chain amino acids. Is that clear? The next one is alkaptonuria. Now, the same similar thing occurs. Phenylalanine is converted to tyrosine, and we know this enzyme is deficient in the PKU. But if it's normal, so phenylalanine gets hydroxylated to tyrosine, and tyrosine can take another path again to go through the formation of different molecules. Malonyl acetate here, but it's going through what's called the homogentisate, okay? And there is an enzyme that converts homogentisate to this malonyl acetate. So the enzyme here is called the homogentisate oxidase, okay? So sometimes you have a mutation in the genes that are coded for this homogentisate oxidase, and the enzyme becomes deficient. So when the enzyme becomes deficient, so again, the substrate accumulates, right? The level goes up, and then they can be excreted out in the urine, okay? And they are acids, okay? So again, it is a disorder associated with metabolism of tyrosine. Okay? So once the homogentisate accumulates in the urine, so basically it will get leaked out, urine, then it can give you a different color like here. This is a patient's urine sample. But if you look at the person after the urine after 1 hour, then it will give you a black color because the homogentisate get oxidized. When it gets oxidized in the air, so it gives a dark color. Imagine you have a baby just born, and then you look at the diaper, and diaper is completely black. That's kind of scary, right? Yeah, no, it is because of the enzyme, the oxidase enzyme deficiency. Okay, so you have a high level of homogeneity in the urine. Okay, so that's a diagnosis. If you see a patient urine sample, you see the NA-oxidase. Yes.
Yeah, so I had a question. So if you look at the pathway, since the deficiency in the homogenistic acid oxidase is blocking it, does that mean that you would have like increased melanin production since it would have to be?
Oh, exactly.
So would you see like darker skin and stuff like that?
That's a possibility. I'm not sure if you have so many other ways you can go. But what we notice, the homogeneity, it's a water soluble. So it can leak out and get excreted out in the urine. Yeah. So you will not get that much accumulation up to the point that you're saying. The melanin, we know you have sometimes in certain conditions you have increased melanin synthesis, but this is not one of those. So we're going to talk about that a little more in the, next year, where melanin for disorder will lead to melanin formation and person get a darker skin. Okay, and which is a possibility if the melanin tyrosine can also accumulate, so tyrosine can take off in different direction. That's what he's saying. But it turns out the homogeneity is water soluble, so it can leak out and you excrete it. So it come out of your urine. It will not accumulate as much as you will see when the melanin synthesis occurs. Okay, so and then the person have a black urine. So if you have a patient and you see a black urine, you can say, "Hoo, that is something out of the scene," right? Is that clear? All right. So again, alkapnuria. So it turns out this lady, older lady, has some issues associated with the enzyme. So you see this black mark, substance accumulated in the vertebra. So she has the issue with the vertebra, and then when you take a look at it, you see this accumulation of these dark molecules associated with the accumulation of homogenetic molecules. Is that clear? And as you see the art color here, accumulation of the, and it usually, the patient will start showing these symptoms at age 40. So, in order to respond to it, so you don't have that much accumulation right away. So it takes time, okay? So then usually the symptoms show up at age 40. And then as you can see, the person has some darker skin color and then so forth. This case, but not as much as you will see in other conditions right away. So it takes about something like 40 years before you accumulate so much of this. All right. So if you don't have any question, thank you, and I'm done. All right. Good.